Hey, good morning, everybody. This is Charlie Goodhart. We're just opening up the go to webinar just so everybody can sign on, and we'll try to get started probably here in about 2 or 3 minutes with the webinar. Well, good morning, everybody. I have 10 o'clock or a few seconds after, so I think we're going to get started with our first PAPA webinar of 2021. Let's say welcome to everyone. I'm Charlie Goodhart. I'm the Executive Director of the Pennsylvania Asphalt Pavement Association. I'd like to welcome everybody and thank you for attending. I'd also like to thank Ingevity, Brian Peck and some of his key colleagues at Ingevity for sharing their knowledge and research findings with us this morning on warm mix additives for warm mix asphalt. To get started, I'm gonna take my webcam. I'm gonna mute my webcam here and take it off a minute. I thought maybe it'd be a good idea just to go through a little bit of, history of a warm mixing with Pennsylvania, and particularly with PennDOT. Many of you know I worked at PennDOT for 36 years, and one of the things I was involved with at PennDOT was trying out, piloting, implementing the warm mix asphalt technology. And really, to give you a little bit of the history, you can see it up on the slide. We actually started back in 2008 with the Asphalt Pavement Quality Improvement Committee. They put a task force together to start the march forward with implementing warm mix technology. And between 2008, 2009, 2010, there were a number of warm mix demo projects completed in Pennsylvania by PennDOT. I know back in 2009, 2010, 2011, because of the influx, and I call it a tidal wave at the time of the Marcellus shale industry, and how they impacted the roads in particularly north central Pennsylvania. When they were fracking, they were hauling water day and night to frack the gas wells. Only way to maintain the roads through winter, down to freezing or even below was to use warm mix asphalt. And I know at the time there was a lot of concern how that asphalt was going to hold up, how that roads and those pavements are going to hold up. And I want to tell you though, most of those roads that were paved at 30 degrees or 35 degrees in winter are pretty much up in Tioga, Bradford counties, up in north and central Pennsylvania. They're pretty much still there. In 2011, then, Everyday Counts come out with a goal from FHWA of doing 20% of the mix with warm mix, and PennDOT adopted that. In 2013, then PennDOT added warm mix as a section with hot mix, with section 411 to Pub 408, which is PennDOT's construction manual. Then in 2016, Deputy Secretary Scott Christie announced at our annual conference that PennDOT was going to go 100% warm mix. And, it would take a couple years because some projects were bid with hot mix, and they were allowed to switch over to warm mix if they wanted to, but that was the goal. Pretty much by now, just about all the asphalt produced in Pennsylvania is produced with the warm mix technology. And in 2019, the association and our technical committee folks worked with PennDOT to update section 400 of the publication 408, which is the asphalt mix section. And we actually eliminated hot mix and warm mix nomenclature from Pub 408. And now we only call it plant mix asphalt. So I don't want to say there's no more warm mix, but because there's still that warm mix technology that's required, but we only call it plant mix now. The other thing is I wanted to cover real quick. There is a Bulletin 15, which is publication, official PennDOT publication 35, which is the qualified products list, which has all the warm mix technologies listed. If anybody wants to know what's approved and what's not approved, you have to go there. There's 4 types of foaming equipment, mechanized foaming equipment that's used primarily with water with maybe some additives in it to make warm mix. But there's also 9 chemical additives and 6 organic additives in there. And one thing we wanted to note that 9 of the 15 additives are also approved as an anti-strip agent. Just a little bit of information on that. Back in 2014, 15, 16, PennDOT did a research study, and it was done by QES Incorporated to perform a cost-benefit analysis of anti-strip additives in hot mixed asphalt with various aggregates. PennDOT was experiencing a lot of stripping problems with asphalt mix, particularly across the northern tier of Pennsylvania. So basically what came out of that was a policy that anti-strip agent was required in all asphalt mixes unless the producer could run the various like TSR tests or whatever to test out of it that they didn't need it. So just about every mix, ton of asphalt mix made in Pennsylvania now is a warm mix, or it has an anti-strip agent in it. The last thing I wanted to cover, like Gary Hoffman thought, who's our Director of Technical Services, thought we ought to just point out that a warm mix is really defined as an approved warm mix asphalt technology. So yeah, there are temperature thresholds, minimum and maximum. You can see that what they are here on the screen. They are by various PG grades. You'll note that as of last year, PennDOT switched over to Massacre as far as nomenclature designation. So you can see that the chemical and organic foaming additives are at a much lower minimum than the mechanical. And there are a lot of, I would say there's a little over 200 asphalt plants in Pennsylvania, and whenever anti-strip the anti-strip requirement was added, a lot of those did move from foaming to using a warm mix additive. So I just wanted to cover that. Now I'll just cover briefly. I'm just about done, and we'll get on with the meat of the webinar. But just want to cover a couple housekeeping items before I turn it over to Brian Peck from Ingevity. If you noticed by now, all attendees are muted, and we're probably gonna have around 100 attendees, and only presenters will be speaking live. We ask you to submit questions via the question pane of the control on your control panel. Type them in there at the end of the at the end of the 3 presentations. I'll sort through the questions and I'll start asking them to the experts, and we'll get you some answers. The webinar is being recorded, and we will post a link if you want to look at it again on PAPA's website. There will be an hour, perhaps an hour and a half. I don't know. We were discussing that, whether it's at least an hour of PDH credits will be issued at the conclusion of the webinar. So now I'd like to I'll introduce Brian Peck. Brian's the technical marketing manager for Evotherm and Ingevity Evotherm in northeastern U.S. and Canada. Brian has, I guess, probably over 30 years. I thought like maybe 50 years, but only 30 years of experience in the asphalt industry. You know, and he's been in sales, he's been in quality control, operations, production, material laydown, etc. So he knows the business, and he's an active member of the National Asphalt Pavement Association. In fact, he served on the board of directors previously, and he's also active with the National Center for Asphalt Technology at Auburn University. He served on their board of directors. So, Brian, I'll let you do the introductions, make a few remarks, do the introductions, and I'm gonna mute myself, and then we'll turn it over to your presenters.
Thank you, Charles. I appreciate the opportunity to partner with PAPA to present this webinar. I also like to take the time to just welcome everyone that has joined us. We really do appreciate this opportunity to share this research that this team has put together. So we really appreciate the time that you've laid out for us. I just want to take a moment just to give a little background with warm mix. You say I was very involved with NAPA, especially when this warm mix was taken apart. Chaired a number of committees there. I know several years ago, IROC in Europe started studying the effects of the asphalt fumes on our asphalt industry workers. And while that was going on, the industry here in the States, led by NAPA, was looking how we could eliminate or even reduce our industry's workers' exposure to these asphalt fumes. The one thing that came out of this ongoing study is that the lowering of mixed temperatures greatly reduced the emissions or the fumes coming off the asphalt mixes. Since then, there's been a lot of different products and methods that have come available for people to use that will allow the producers and contractors to utilize warm mix at greatly reduced temperatures. And these products will allow the contractors still to produce, lay, and compact asphalt mixes that meet agency specifications. The question down in front of us that I hear a lot going around is that agencies, what effect does producing warm mix at lower temperatures have on asphalt mixes? And this is where this webinar and this research has really concentrated. In this webinar, we're going to look at the effects of warm mix asphalt has on binders, asphalt mixes, and pavement life. So with all that said, I'd like to introduce our 3 speakers today. I want to introduce all 3 of them, and then we'll go on and we'll get started. Our first speaker today is going to be Dennis Muncie. Dennis is our performance manager for binder technology and the Ingevity pavement technology. Since 2016, Dennis has 33 years background in the asphalt industry operations, business development, and technical services, and has led him to focus on the maintenance and rehabilitation product development for Ingevity. Dennis received his bachelor's degree in science and chemistry from Indiana State University. Our second speaker, Dennis, is going to talk about the binder effects of warm mix on the binders. Richard is currently our platform manager with Ingevity Pavement Technology, where his focus is warm mix asphalt and asphalt mixture performance test. Richard has a BS in civil engineering from Texas A&M University and an MBA from Midwestern State University. He is a registered Perf engineer in Texas, Kansas, and Oklahoma. His talk is going to be based on the mixed performance and what's. Jason Rosado, our last speaker. Jason received his doctorate degree in civil engineering from Iowa State University with the specialization in asphalt materials. Prior to joining Ingevity in 2010, he worked for the Naval Facilities Engineering Service, where he helped manage the airfield pavement program for the Navy and Marine Corps. At Ingevity, he currently manages the performance testing laboratory in Charleston, which is used to create new products for highway construction applications. And I really appreciate these three guys of all the work and the hard work they put into this research and putting things together and put it in a form that we're going to see today. So with that said, I'd like to go ahead and let Dennis get started with his presentation.
Okay, thank you, Brian. Is the presentation up?
Yes, sir.
Okay, very good. Well, good morning, everyone. Thank you for this opportunity to present some of the recent work that we've done as regards to warm mix asphalt and how lower short-term aging temperatures improve asphalt binder performance. I'm going to turn myself off here. So with that, let's get started. So on the agenda today, there's really three main areas that we're going to talk about. Just a little refresher course maybe to most of you about binder age hardening and some of the activities that promote binder age hardening. Going to look at a little bit at some initial work that we did and how varying rolling thin film temperatures impact the high temperature performance of binders from a rheological sense. And then we're finally going to get into the meat of the research that we've done recently, where we're looking at varying rolling thin film temperatures plus long-term age performance of the binders. So what influences binder age hardening? Well, there's really two distinct conditions during the service life of the asphalt binder or of the pavement structure. We've got this short-term aging that occurs during production and application. That's where the binders are exposed to very high temperatures. The film thicknesses are very small. So there's a lot of oxidation going on there, a lot of volatilization going on, and that's a significant contributor to binder age hardening. The other condition is the in-service aging. You might think of this as being environmentally dependent. Once the pavement is down, depending on your geographical area, that really controls how the binder is going to age. But another unique consideration about these two conditions is that the production and application being process dependent, that there's a level of controllability there. Whereas once the material is down with the in-service aging, which is environmentally dependent, that's what's going to happen is what's going to happen. And we have a lot of good predictive tools out there today, but nonetheless, it's still predictive. So, and these two conditions are well recognized within the industry and have been for a number of years. And as such, for the short term, this short term high temperature aging, we have a standard from the rolling thin film oven. So the binders are conditioned through this rolling thin film oven at an elevated temperature for a short period of time and tested after that conditioning period, and the PG grades are, or the binders are classified for certain PG grades depending on the binder stiffness. And likewise for the in-service aging, we have the pressure aging vessel, and that's another standard out there today. And it's a lower temperature environment, a longer aging time, simulating multiple years of service out in the field. But one thing about this, at least from the rolling thin film standpoint, how does it correlate to these newer technologies, and in such warm mix asphalt? So in a warm mix asphalt production scenario, the binder may not ever see 325 degrees Fahrenheit. So, you know, that's a little bit of a drawback on trying to categorize what the performance of a warm mix asphalt might be. So with that in mind, we took a look at various rolling thin film temperatures impact on binder aging or binder hardening, sorry, binder hardening. So what we have in this graphic, we monitored G star divided by sine delta at 64 degrees C. So we have binder stiffness over here on the y-axis. And then on the x-axis, we have conditioning hours. And so the standard rolling thin film oven temperature is 163 degrees C. So we've got the original binder here. After the rolling thin film cycle at the standard, you can see that the binder increases in stiffness. And then as it goes through the several PAV cycles, here's one PAV cycle, here's two PAV cycles, that the binder continues to get stiffer over time. And that's well known. But what is interesting here is, so we ran a rolling thin film. Everything was standard conditions except for the oven temperature. And in this scenario, the oven temperature was 135 C. And you can see not as much binder age hardening occurring after the rolling thin film. And then we've got this parallel behavior, parallel line behavior as it goes through one PAV cycle and two PAV cycles. So this is an indication right here that most or a significant portion of the binder age hardening differences occurs during this high temperature exposure during the rolling thin film. So so there we have the standard and the lower temperature. Now we ran a rolling thin film at 177 degrees C or 350 degrees Fahrenheit. And as you might expect, the higher exposure temperature, greater binder stiffness after the rolling thin film. You can see that considerable binder stiffening here. And then once again, we get out here into the PAV cycles, and these relatively parallel. So again, that's an indication of during the rolling thin film, or that short-term exposure to those high temperatures, that's where the significant portion of the binder hardening is occurring. So if we look at the numbers, here's just a summary table of those three conditions that we just looked at. We've got the standard rolling film here in the middle. We've got the lower rolling thin film, which is 50 degrees lower. And then we've got the rolling thin film oven exposure temperature that was 25 degrees higher than standard. And so what we have here, I've just tabulated what the aging rate is in kilopascals per hour for each one of these conditions. So from the original to the rolling thin film conditioning, we have a stiffness rate change of 1.24 kilopascals per hour at the standard rolling thin film. At the lower temperature rolling thin film of 135 degrees C, we have a 0.77. And then at the elevated temperature of 177 degrees C, we have a 2.32. Now those numbers may or may not seem significant per se, but if we come down here and look at the rate change relative to the standard, so the lower temperature reduced the rate of binder age hardening by 38%, which that's a pretty significant number. And then in this scenario, the higher temperature rolling thin film at 177 C increased the rate of binder aging or age hardening by 87%. So that's a very, very significant figure there. So one other thing that we looked at from a high temperature perspective was mass loss. And as Brian alluded to, you know, there was a lot of work done with fume exposures and such. So what we have here, we looked at 3 different binders. We have 2 PG6422s and a 5828, and we recorded mass loss at various rolling thin film temperatures. So we have the standard rolling thin film here, standard rolling thin film temperature of 163 here, and then or 325 degrees Fahrenheit. And we reduced the rolling thin film temperatures by 50 degree increments in each one of these vertical data sets. So that would be 275, 250, and 225. If I'm doing, no, I'm sorry, I did my math wrong, but these are 50 degree increments. And as you can kind of visually see that there's lower mass loss rate of change at these lower temperatures, and then it comes to a point, and then we have this accelerated increased rate of change of mass loss, so that at above these temperatures, the mass loss really kicks off. And that would be at the inflection point. So I've added a couple inflection points, or an inflection point for each one of these graphics here, and you see the different color coded. And it just so happens that with these binders anyway, that these inflection points from the lower rate of mass loss to the accelerated rate of mass loss happens in this what would be considered a typical warm mix production range for a PG6422. It's in that 240 to 275 degree Fahrenheit range. So we found that was very interesting also. So with this high temperature work, it led us to more questions, and of course we wanted to answer those questions. But a couple of the key questions were, well, how do these lower short-term temperatures into this warm mix asphalt region impact the binder's low and mid temperature performance? You know, we get down into that cracking performance realm, which is in a lot of cases, that is the one of the critical mechanisms of failure. And then the other question was, well, does the typical PG grading of only 24 hours or 20 hours of PAV aging show the value of these lower short-term temperatures? And so those are the 2 questions that we're going to try to answer going forward. And with that, we conducted a study, and we're going to look at 4 binders from that study that we feel are fairly significant here. So here's a table of the binders that we used. So we used a PG 6422, and we conducted its rolling thin film at the standard, 163 degrees C. Used the same 6422, and we conducted its rolling thin film at 177 degrees C. We have another binder here, which was a binder blend. It was the 6422 used in the above examples. We added 10% of a synthetic wrap, and that synthetic wrap was laboratory produced, where it went through short-term oven aging, like the rolling thin film, and then low temperature aging for multiple days until we got to I believe it was a PG 87 minus 17. And so this blend has 10% of that material and 0.5% of a chemical warm mix additive. Now, now we're getting into the warm mix environment. So we ran its rolling thin film at 135 degrees C or 275 Fahrenheit. So that's a 50-degree lower rolling thin film than the standard. And then our fourth binder is a PG64 with 25% of that synthetic wrap and 0.5% of a chemical warm mix additive. And again, its rolling thin film was conducted at 135 degrees C to represent a warm mix environment. And so after each one of those rolling thin film conditions, we ran it through multiple PAV cycles, and the PAVs were conducted at 100 degrees C, and we did increments of 20, 40, and 60 hours of PAV aging. And then at each one of those increments and throughout this different types of sampling or different conditions, we're going to look at the PG low critical temperature, which the PG YY value. We're going to look at delta TC, and then we're going to look at Glover-Rowe parameter after each one of these aging conditions and compare those values. But before we go into the comparison, we kind of need some performance criteria. And here's a summary table that was presented by Jeff Rowe, and it's got multiple authors, I would say, from these recommendations. But from a criteria standpoint, we've got a crack warning and a crack limit. And so for delta TC, the recommendation is a negative 2.5 for a crack warning and a negative 5 for a cracking limit. And then on the Glover-Rowe parameter, the crack warning is 180 kPa and the cracking limit is 600 kilopascals under these testing conditions. So now we have the criteria to compare these binder performance going forward after these multiple or these various aging conditions. So the first one we're going to take a look at is a PG low temperature grade versus hours of PAV conditioning. So we have the four binders that were listed on that chart. We've got the 6422 at the elevated temperature is red, 6422 at standard rolling thin film temperature is yellow, and the 2 warm mix scenario with the 10% wrap binder is the dashed blue square, and the 25% asphalt binder replacement with the warm mix additive at the lower rolling thin film temperature is the solid blue line. So after the rolling thin film conditions listed here, we ran, again, just the 20, 40, and 60 hours of PAV aging, and then looked at the PG low temperature value for these. And and here's the specification line or the criteria of -22 for these binders. And a couple things unique here is at the standard PG testing conditioning periods with the standard of the 20 hours of PAV, we have this cluster of binder performance here. And of course, with this cluster, there's a small margin between the high and the low that you would expect that these binders would perform very similar long term. But as you can see, as we age these materials from one PAV cycle to 2 to 3 PAV cycles, that these materials started to diverge a little bit. And that actually this material, even though it had the 10% synthetic wrap replacement binder, but it was conducted, its rolling thin film was 135C, it still maintained a -22 value out to 60 hours of PAV aging. Whereas the standard, which is this yellow, crosses over that -22 criteria line at about 35 hours. Likewise, the same as the 25% wrap replacement binder that was done at the lower rolling thin film temperature. The other thing to note too is that you know, this is only 25 degrees increase Fahrenheit increase in rolling thin film temperature versus a standard, but you can see the level of damage that was done to this binder from a low temperature criteria. It actually fails the -22 criteria at the 20 hours of PAV aging. So the next set of criteria or data that we're going to look at is delta TC. So we have delta TC on the y-axis, and again we have the hours of PAV conditioning on the x. And we have the same legend here. So the red is the high temperature, yellow is standard, and the blue are the lower warm mix temperatures. And as you might expect, if you've seen any delta TC data, that as they're aged longer and longer in PAV condition, that the delta TC decreases. And that this 6422 that was done at the standard rolling thin film, you can see that after 2 PAV cycles, it's down here, it crosses over this crack warning criteria, and then you know, eventually gets stiffer over time. Excuse me. The other, see a little bit of variability here, or a little different behavior with these warm mix or these lower temperature rolling thin film materials. Both of these materials pretty much maintained good delta TC numbers throughout the 60 hours of PAV aging. And then likewise, as we saw earlier, that the higher temperature rolling thin film has degraded the binder, and it's already passed its crack warning criteria for delta TC after one PAV cycle. So again, we're kind of seeing a commonality here from a low temperature binder performance characteristics. So the next area that we're going to look at is Glover-Rowe, and just the Glover-Rowe parameter, sorry, and just a little bit of background on that. A researcher, I believe it was in Pennsylvania, Kendall, back in the mid to late 70s, conducted a lot of research on cores from pavements, and of course back in the mid 70s there wasn't a lot of rheological equipment back then, so he correlated ductility with this testing conditions to pavement condition, and what he found was through multiple pavements that he studied throughout the years, that there was a good correlation between ductility and pavement condition. And as ductility reduces, so does pavement condition. So that work was followed up by Dr. Rowe from TTI, and he and his group published a document, FHWA document, in 2005. and now there is rheological equipment. So Glover correlated this ductility parameter, like Kendall did, with a rheological parameter. And you can see a very good correlation here between ductility and this rheological parameter. Glover's rheological parameter was then transformed a little bit by Dr. Rowe. And in 2011, in a AAPT paper, Dr. Rowe presented this a little bit of a variant from here we have Glover's equation, and now we have Rowe, and so and now it's termed the Glover-Rowe equation. And so it's a stiffness parameter of the binder, and as materials age, they get stiffer and stiffer, and so the Glover-Rowe value gets higher and higher. And we saw from that table that the crack warning is at 180 kPa, and then the cracking limit is 600 kPa. And this is some of the terms that they've defined. So Glover-Rowe, here's an example of how Glover-Rowe is presented from a research level. And so at each one of those PAV conditioning temperatures, the Glover-Rowe parameter or the rheological parameters were tested on those binders. And here we have a plot. This is termed a black space diagram. Here we have a plot of the log of G star, which is the rheological property, versus phase angle. And so each, I'll take this yellow dot. So here's the 20-hour PAV result, the 40-hour PAV, and the 60-hour PAV. And on this graphic, if the binder is softer softer than 180 kPa, no block cracking. Once it gets somewhere between 180 kPa in binder stiffness, that there's the potential for the material to start to crack because of its lack of flexibility. And so, and when it reaches the limit of 600 kPa, then the binder, we're going to see block cracking for sure up in this area. But this is, in general terms, this is how all binders behave. They start out softer with a higher phase angle and a lower G star value, and then they, as they're ran through multiple PAV cycles or any type of binder aging cycles, that the phase angles decrease, and the G star or the complex modulus of the material also increases. So that's how you might see Glover-Rowe in a classic environment. What I'm going to show you now is a little bit different method of looking at the Glover-Rowe parameter. You might think of this as a pavement deterioration curve, kind of the same basis for that. So on the y-axis here, we've got the percent remaining Glover-Rowe service life. And then down here on the x-axis, we have the PAV conditioning hours. So 0 PAV conditioning hours, that's the rolling thin film binder. And just as in a pavement deterioration curve, once the material is laid, it still has 100% of its life left. And as the years go by, this is for pavement deterioration. As the years of service life go by, the level of pavement quality decreases. And just like that, in this in this case, this is the binder rheological properties, again, from these 4 binders. We start out with the rolling thin film at 100%. And here's our criteria for the crack warning, which is 180 kPa, which is basically 70% of its life. And then we go down here and at 600 kPa, which is the crack limit, that is 0% of its life. So once the binder, through all of these conditioning cycles, once the binder reaches 600 kPa, in this example, it's considered to have no binder life left, or binder service life left. So with all that being said, and I kind of apologize for that, but so let's just kind of look at the data here. So the standard 6422 going through the standard rolling thin film, you can see its curve. It's 100%. It crosses over the crack warning at about 37 hours of PAV aging, and then it's going to hit the crack limit at about 67 hours of PAV aging. You can see relative to that, the exposure to the increased temperature, it drops off significantly, or several hours of PAV aging. And these materials that were exposed to the lower short-term aging temperatures, much like a warm mix production temperatures might be, extends the number of hours of PAV to these various criteria. In this example, that really, it doesn't look like much, but that's about a 35% increase in binder, or in the number of hours of PAV conditioning to reach this criteria. So we've got a 35% increase in service life with these examples. So just, and then likewise down here to these crack limits, that's in the 30 to 40% increase in service life between the standard rolling thin film and these lower rolling thin film temperatures. So I want to show one more graphic. This was just another 6422 from the mid-continent region. Same graphic, same percent remaining service life here on the Y, and PAV conditioning hours here. We took this is a different 6422, exposed it to 177 degrees C rolling thin film, the standard at 163. And then this lower rolling thin film, again, we added 0.5% of a chemical warm mix additive and ran it through multiple cycles. And you can see, again, that this is a different 6422, and its behavior is a little bit different as far as the actual values. I think I said earlier, the standard crossed over this 180 kPa warning limit at about 37 hours. Well, this one crosses over at about 50 hours. So, of course, different asphalts behave differently, and there's different qualities of asphalts out there, per se, on a comparative basis. But again, we see the same trends from this exposure to these rolling thin film temperatures. Elevated temperatures degrades the asphalt much quicker than the standard, and then we reduce these short-term aging temperatures down into this warm mix area, And again, we see this 35 to 40% increase in the number of hours of PAV conditioning to reach that criteria. Okay, so just to kind of wrap all this up. So in summary, if these lower short-term aging temperatures lead to, and these are just from the examples that we've been able to discover and that I hope I showed throughout this presentation, is that we have a reduction in binder mass loss, which really equates to less binder waste during production, less of it going up the stack. So we've got less environmental impact. We saw several examples through low temperature PG grade delta TC and Glover-Rowe parameter that the improved binder low temperature and cracking performance occurs with these lower short-term aging temperatures. There was some indication that these lower short-term aging temperatures compensate for increased wrap usage. Less of the volatiles are going out of the asphalt and staying in these blends, and that is compensating for the wrap stiffness. We saw a couple examples where the 25% wrap blend actually performed very similar to the neat virgin 6422. And then in all of these, or several of these examples where we looked at PG grade delta TC and Glover-Rowe parameter, we saw examples of extended binder service life. The number of hours of PAV aging to reach any of those criteria was extended after the lower short-term oven aging temperatures. So with that, if we see all these benefits, then why isn't the industry more focused on reducing production temperatures? And I'll just kind of leave it with that. And thanks for your attention. And I guess probably the questions are going to be tabulated and answered later. So thanks again for your attention, and hopefully that provided some good insight.
Thanks, Dennis. Can everybody hear me?
Yes.
Yes, sir.
Okay. I'll get this into, you see the right screen now? Okay.
Balanced mix design.
Very good. Well, so now everybody's kind of seen from a binder testing point of view what the impact of using warm or cooler temperatures on the asphalt is. And so this next section is going to be a brief look into the impact on the balanced mix design. Now, we did this work about 18 months ago, and 18 months ago, the knowledge around how to condition samples, what to actually do for the balanced mix design was very unclear. It's becoming more clear now as more research has been done and more studies have been published about all of that. But so anyway, we'll give you a little bit of a point of view of what we were looking at about a year ago. So anyway, we're going to jump off into the balanced mix design here. So what does the balanced mix design do? Essentially, what it does is ensures that you have the right quantity of asphalt in the mix right at the point of laydown. What it really doesn't do very well now at this point, it doesn't really address the quality of the asphalt used or consider any of these impacts that Dennis has talked to you about with regards to the long-term aging or the temperature of the binder in the mix on the mix performance. So and then, as I'm sure you've probably seen, NCAT has done a tremendous amount of work. They've got workshops that they've presented around the country, and in conjunction with the federal highways, they've defined what balanced mix design is, and that's what's showing up on your screen now. And what they really talk about in this definition is about appropriately conditioned samples, taking into consideration mix aging, traffic, climate, location within the pavement structure, and those types of things. So in my opinion, and in the work that we did, the understanding how to appropriately condition samples during the mix design process and to how to evaluate them and what tests to use is all still somewhat up in the air. The mix aging piece is really needs to get resolved here soon, and there's a bunch of work underway now trying to answer that question in more detail. So as everyone is aware, the volumetric mix design is primarily what we've been doing with SuperPave. It does a really good job of proportioning the aggregates in the asphalt binder. It's got a few issues with regards to the aggregate bolt specific gravity, the accuracy of determining that, and the variability of determining that that value. So then you and then it also helps you determine how much asphalt is supposed to be in there. So we get the quantity of asphalt pretty good, but we still have a question mark by quality. And so then you throw in all of these things like modifiers and additives, like say a chemical warm mix additive, which is highlighted here. There's all sorts of additives that people want to put in asphalt mixes, you know, from PPA to REOB to the recycled asphalt pavement to shingles. And then you've got polymers, rejuvenators, fibers, now plastics. Those types of things are all starting to show up in asphalt mixes now. So how do you handle that in the volumetric mix design process with you know, trying to understand how these new materials are going to impact things? So anyways, all that being said, there's still questions around the balanced mix design. So, you know, so first off is, you know, which performance test are you going to use? You know, how are you going to use these particular tests? What aging and conditioning protocols are you going to use? Already talked about those a little bit. You know, and then things that still need to be answered is where do they fit in this mix design process? You know, what criteria are you going to use in the specifications for these particular performance tests and in the balanced mix design process? You know, can you use these performance tests in the QC QA activities that during the laydown and in the production of the mix? So all good questions. I don't have all those answers here, but what we're going to do is take a look at kind of an initial look at what the impacts are on a couple of tests. And the first test that we looked at is on is the ideal CT test. That particular cracking test has gained a lot of ground recently. A lot of different states are using that or taking a look at it. It's been standardized through ASTM. And then also the Hamburg wheel tracking test. That test is also standardized through AASHTO, and it's widely used in the United States. And so we thought those two tests would be a good way to take an initial look at the impact of warm mix and hot mix with regards to the balanced mix design. So the design that we looked at is it's a mix design that was prepared by a laboratory in Dallas, Texas, TSIT. It's a standard SuperPave Type C mix that was done. It's a Texas DOT mix. The aggregate materials, pointer here. These are all the aggregate materials. We ran combinations hot and warm using, when we did the warm, we used the Evotherm chemical warm mix additive P25 and M1 at 0.5%. The binder was a 7022 that came out of Jebro, out of Waco, Texas. This mix also had a fractionated wrap in it, as well as a mineral filler, and you can see the quantities of those listed right here in the bin quantity. So this had about 3.5% of the mineral filler and then 17% wrap. This is the 45 power curve on this particular blend. You can see that it does meet all the SuperPave criteria. This is what you would call, from an Asphalt Institute point of view, would be considered an intermediate type blend. So in the work that we did, we made a lot of different types of mixes, and we're going to show you 4 of them here. The first off is we did just a hot mix, what we called standard air voids. We mixed and compacted these samples at we thought something that was reasonable for a hot mix, which was 300, and then we compacted them at 275 Fahrenheit. We used 5.2% on the asphalt content, and then we normalized all the air void targets, or all the air voids for the CT samples to 7%. There's a way to do that now. The folks at TTI have come out with that procedure, and it's relatively easy to do if you don't exactly have 7% air voids on your CT samples. And then also know that the air voids has a huge impact on the value of the CT index. So in this hot mix, we did not have any sort of warm mix additive in this. Then one of the things that we heard in the past was that balanced mix design was really just code for adding more asphalt to the mix. That's essentially what that means. And so we thought we would look at that as well. So we added 0.2% more AC in this mix, kept the other criteria the same, except for the asphalt content. And then we put two mixes together using two different chemical warm mix additives, as I stated, at 0.5%. And we dropped the mixing compaction temperatures down into those ranges that Dennis talked to you about earlier, which is kind of in that warm mix sweet spot area, around 265 Fahrenheit. And then we kept the asphalt content at around 5.2. And so we'll take a look at what the impact was on some of these balanced mix design tests. The first one up was the ideal CT, and as I already mentioned, this has been standardized through ASTM, and that's the number there for it. The next, this slide gives you an indication of what the impact was. We had at least 8 and then many times more samples in this to understand kind of what the variability of that test is. So we had at least 8 replicates on each one of these sets. But what you can see here is that in general, the first observations is that this is a really good mix from a CT cracking point of view. It's got very high numbers. But what you can see here is that you get a slight boost when you increase the asphalt content 0.2%. It goes up. You get a very similar boost when you drop the temperature and you use a warm mix additive. That's so from basically from a cracking index, you see a better index value when you add more asphalt, and then also when you use a warm mix additive. Another thing that I would point out is that, and I've seen this on multiple sets of test data that we've generated, is that you typically see a lower variability in the cracking tests when these are produced warm. So it's not hugely different, and you can't say from a statistical standpoint that any of these are actually different because all these error bars cross. So but you can say in general, the index value tends to improve as you use a warm mix additive or you increase the asphalt content. This is another view of some of that same data, and this also illustrates the less variability when you produce warm. The blue one is the warm mix samples that we compacted and tested. And you see here again, you get a bit of an increase when you just by dropping the compaction temperature. The next look that we had was the Hamburg wheel tracking test, and that's been standardized through AASHTO, the T324. I'm sure many of you are familiar with that test. And move to the next slide. It takes a minute to pop up here. This particular test, we ran these same combinations again on the Hamburg wheel tracker, targeted 7% air voids. The water bath temperature was 50 degrees Celsius. And on this particular set, I combined the warm mix additives into the same line because they were both essentially the same. But this was the hot mix line, this top line, and this is the warm mix in the blue line, where it was compacted at lower temperatures, and then this bottom yellow line where we added the extra asphalt. You can begin to see the beginning of a stripping inflection point here, and it also started to tail off towards the end of the test. So it was getting close to that 12.5 millimeters of rutting. So although all of these mixes did fine, yeah, out to 20,000 passes, you can see that in general that there's really no change in performance from a rutting perspective when you use warm mix. And then you can see that as you increase the asphalt content, there is a risk of, you know, a bigger potential to start rutting depending on the mix. And so since we are able to do that in our laboratory, we extracted and recovered, and then Dennis conducted all of the PG analysis for all of these binders and that we've tested in the CT and then also in the wheel tracker. So this is kind of a summary of what we found here, in that you can see that there was a slight drop across the top on the top side of the of this binder. And remember this, we started out with a 70-22. So and then also you can see that we found on the bottom end, we gained a couple of a degree or so on the bottom end. And having that extra degree or so on the bottom end is impactful, because it can help you with regards to cracking and to delay the cracking in a mix. So there was really no difference in that on the hot mix or the hot mix with extra asphalt, but you did see that improvement on the warm mix additives. So we're moving on. Just to conclude here, essentially what we've shown here is that the balanced mix design really shows you currently the process that's in place. It really just shows you what the performance of the mix is at the point of laydown, at that 20 hours of PAV aging, as Dennis has already described. And then other things that we've seen here is that when you use a warm mix additive, you can typically see an improved ideal CT result or a cracking result when the mix is mixed and compacted at warm mix temperatures. Also, you can see that that you get just as good or better rutting performance when you use a warm mix additive versus adding extra asphalt, and at least it was in this particular case. And then as we transition into the next speaker with Jason, he'll show you how these extended binder and mix aging and warm mix pavement through the structural analysis, he will show you how these things carry on through the pavement structural analysis piece. So, and you can begin to see the benefits of using a warm mix additive and lower temperature production on the longevity of the pavement structure. So, if warm mix can extend your pavement service life, why aren't we all using a warm mix additive? So, with that, I will. I think I can do this. Yeah, there we go.
Thank you, Richard, and I want to thank you for sticking on for this the third piece of this webinar. Today, I'll talk about quantifying the benefits of warm mix asphalt to extend pavement life, and I'll do this through two different predictive models, and then also show some real life field data of comparing hot mix and warm mix as well. So to kind of summarize where we've been today, we listened to Dennis talk about the benefits of reducing the temperature on the binder side of things, looking at reduced RTFO temperatures and the impact on long-term aging using the PAV, and the impact on properties such as Delta TC or the Glover-Rowe. We just listened to Richard talk about a balanced mix design approach, looking at the ideal CT in the Hamburg and the impacts of lower production on those properties, whether it be the CT index or rutting. And then this final piece will be an integrated approach using fundamental material properties and looking at either finite element modeling of the pavement using FlexPave, or pavement performance prediction equations to look at how lower production temperatures impact performance. And some background information here. Oshoni in 2019 published a paper on developing a framework for performance-related specifications for asphalt pavements. And that study focused on differences in fatigue performance due to variation in the as-built conditions. And the two conditions they looked at were air voids and binder content, looking at various ranges there. And then the metrics they used were two fatigue life prediction equations, and then two advanced ME methods. And then they looked at the expected life difference concept to make comparisons. And I thought this was a fairly robust approach, so I wanted to see how warm mix compares using this type of methodology. And so the idea of using this expected life difference is essentially the fatigue life of a warm mix asphalt pavement divided by the fatigue life of a hot mix asphalt pavement. And so if you have a value of greater than 1, you certainly have the ability to show the benefits of warm mix asphalt pavement in terms of a predictive analysis. And if you can extend your pavement life, then that certainly has further trickle-down effects by reducing the life cycle cost analysis of that pavement as well. And so this approach that I've talked about will be an integrated approach looking at material property inputs, the pavement structure itself, traffic loading, and climatic conditions, and then that impact on the performance prediction models. And so to get started here, we first need material property inputs in order to make these predictions. One of the first inputs is the dynamic modulus of the mixture. This will give you the linear viscoelastic properties of the mixture. You can build your master curve out of the data. It's ran at 3 temperatures and 3 or 5 temperatures, depending on which procedure you use, anywhere from 3 or 4 frequencies up to 6 frequencies, depending on the test method. This data is used in both FlexPave and the AASHTO Pavement ME software. It's one of the main inputs. The next test is a direct tension cyclic fatigue test. It's typically ran at the fatigue temperature of the binder based on the binder test. It's ran at 10 hertz in 4 strain levels, and then the data is further analyzed to determine the fatigue properties of that mixture. The final test is a stress sweep rutting test. It's ran at 2 temperatures with a confining pressure and 600 kilopascal or 87 psi deviator stress, and this is used to characterize the rutting propensity of the mixture. And so out of these 3 tests, you can either get some index-based properties or mechanistic properties that can then be used in pavement analysis or pavement predictions. You may notice that there's multiple test methods for the top 2. Basically, those are small scale samples or larger samples, depending on what testing you would like to do, and if you have lab produced mix, plant produced mix, or cores. And so out of the dynamic modulus test, you get your E-star parameter, which is used for your mechanistic design. You can also obtain a Glover-Rowe mixture parameter, which has a relationship to cracking of the mixture. Out of the cyclic fatigue test, you can get the D sub R, which is a mechanistic fatigue property of the mixture, which is used in FlexPave. And you can also get the SAP parameter, which is a cracking index parameter, and there's various criteria currently around that as well, based on traffic level. And finally is the rutting test, where you can get the viscoplastic strain, which is used for looking at pavement predictions in terms of rut depth, or you can look at the ATR, which is the allowable traffic for rutting, which would be your index-based property, to just look at specific mixture characteristics. The software is available from FHWA. There's 2 different Excel spreadsheets, one for cracking and one for rutting. The website is listed there in the middle of the screen. You can basically input the number of tests you conduct. You then input your VMA, VFA. You can load your dynamic modulus data, load your fatigue data. Once you load your data, it's analyzed for, in this case, 3 specimens. You can get your output here on the left, which can then be used as inputs for FlexPave. Here's typical fatigue data that you would get out of there, which is your C versus S curves, or your G sub R versus N sub F, which would be your fatigue curve used for FlexPave as well. This modeling is all based off viscoelastic continuum damage mechanics. The spreadsheets certainly make it easy to do the analysis. Once the analysis is done, the data can then be output very easily. And so it's used in this output in this form, and then can be saved to a CSV file, which is then uploaded into FlexPave to do the payment analysis. And so out of all of this, we've used the AMPT to characterize the mixtures. We've analyzed the data. You can either compare mixtures individually using the index-based properties, or you could then incorporate these mechanistic properties into the pavement structure, and then look at performance predictions considering pavement thicknesses, traffic, and climate. And so the example I'm going to show today comes out of a TRB paper by Wang et al. It was published in 2016. This particular pavement structure was in Manitoba, Canada. It was a 4-inch thick pavement. Each lift was 2 inches thick. The bottom lift contained 30% RAP. The top lift was a virgin mix. Both lifts contained a 5828 asphalt binder. And Manitoba looked at 3 different warm mix additives. And then this mixture was then characterized using FlexPave, and also there's real life cracking data as well. And this mixture was constructed in 2010, so you have about 6 years worth of field data on this particular pavement. And so after 6 years, you have your observed field data on the left, and you can see that the control mixture is somewhere in the middle. Compared to some of the warm mixes, the Evotherm warm mixture performed quite a bit better in the field versus the control mixture, more than 50% better. In terms of the predictions, the prediction more or less rank ordered what was observed in the field with there's a slight switching between the control section and the Inver section, but for the most part, what FlexPave was able to model occurred in the field. And I thought this was quite promising. If you were to look at the data just in a different perspective at the end of those 6 years, in terms of what happened in the field, you saw a 92% decrease in percent cracked area in that Evotherm pavement section compared to the control. If you look at what the modeling said, it was a 25% decrease. And you may see that there is some discrepancy there, but that has to deal with the fact that the FlexPave is not calibrated yet to field performance, and so there of course there will be some sort of shift, but it's quite promising to see that what you can use the modeling for to predict performance. And so looking at this data, this intrigued us a little bit, so we wanted to see if we could create our own data set. And so we have a study underway in Tulsa and Charleston where we're making dynamic modulus and these fatigue samples. And there will be 4 mixtures tested. The first mixture will be the hot mix at 8% air voids, and that can be compared directly to a warm mix asphalt pavement at 8% air voids, looking at a 50 Fahrenheit reduction in compaction temperature. Mixtures 3 and 4 are to look at what the impacts are of reduced temperature, but what's the impact of air voids as well. We know that a lot of these additives do provide better field densities, and we realize that happens quite often in the field. So is there some sort of additive effect of improved density and lower production temperatures. There's plenty of literature out there that shows that you see at least conservatively a 10% improvement in pavement life if you see a 1% improvement in air voids. There was some literature from FHWA and NCAT that said that. We have another mixture we're looking at from Kansas. It's a hot mix at 350F. We'll be doing dynamic modulus, cyclic fatigue, and 4-point beam fatigue, and comparing that to another a warm mix asphalt mixture. It's not true warm mix being 295, but it's certainly 55 degrees lower than what they were currently producing, and looking at the same properties. And these samples are currently being tested, and some of the data has been analyzed, but it has not been compiled yet. The final set of mixtures we're looking at are a hot mix at 325, another hot mix at 300F, but with a rejuvenator, and then a warm mix asphalt mixture, looking at the same sort of testing regime to see what the impacts are of production temperature on pavement predictions. And then, like I said, we'll get these pavement designs from the various agencies. We'll be looking at FlexPave along with ASHTO Pavement ME, and that's where the fatigue data comes into play, is in order to calibrate that the fatigue coefficients in Pavement ME, you need 4-point beam fatigue testing at 3 temperatures and 4 strain levels. And that's because the current coefficients in Pavement ME are based on modified, basically essentially neat binders. So in summary, there's existing data that suggests improved fatigue performance with Evotherm warm mix asphalt mixtures. We've got several research studies underway to look at material property inputs and what those impacts are on warm mix asphalt temperatures, and also improved density on field performance. And some may be saying, hey, why, there's got to be more data out there. I mean, warm mix has been around for 20 years now. It's been around since early 2000. One of the reasons I showed this Manitoba data was because it links pavement modeling with field data, and I thought that was a very interesting concept that one could certainly use to quantify the benefits of lower production temperatures. These experimental ranges come from NCHRP report 843. It's the long-term performance of warm mix asphalt mixtures. This project was started in 2011. It finished in 2016, and the report was published in 2017. But this project looked at warm mix asphalt mixtures compared to a companion control, a whole variety of different unmodified binders, modified binders, wrap, with and without some sort of liquid anti-strip or lime, various aggregate types, various traffic loadings. And so I went through this report and I mined the data, because this report contained the following data, and I'll call it a network level analysis, because I looked at the average of 15 projects. The various ages of these pavements at the time the data was reported was anywhere from 3 or 4 years old up to 9 to 10 years old. And so what you can see here is that the 3 distresses they looked at was wheel path longitudinal cracking, transverse cracking, and rutting. So if you kind of pool all the data for the hot mix and the Evotherm warm mix at the time the data was reported, in terms of rutting, there's minimal impact, if essentially no impact of rutting when making a mixture warm. If you look at the wheel path longitudinal cracking or transverse cracking, there's a 24%, I'd say, if you look at both of them, about a 25% improvement in cracking resistance. And something to think about there is if a typical overlay life lasts 10 years and you can get 20% improvement or 25% improvement out of a warm mix asphalt pavement, that could be anywhere 2 to 3 years of additional life. And then what does that impact on your rehabilitation cycle, your pavement preservation cycles? So here's some real life field data. There's also additional field data that's currently being collected through the LTPP program, the SPS 10 sections. There's 8 states in the US with Evotherm hot mix control pairs. Right now, the current payment age is 2.1 years. So there's not a lot of long-term data yet, but there will be more to come as years go on. The final example I'll provide is a mechanistic empirical approach. This is a simpler approach. You don't need some sort of finite element software to do this sort of analysis. You can use just some fatigue life prediction equations. So here's the pavement cross-section that I use. There's really nothing special about this pavement cross-section other than this was the same cross-section that was used in that Oshoni paper. I used Pave Express to determine that the tensile strain at the bottom of the AC layer. And I assumed that there was full bond between the layers when doing the layered elastic analysis. And then the AC surface layer, I was able to do some data mining, and I looked at warm mix versus hot mix mixtures from a variety of research projects. And these research projects are listed here. These come from the literature, some reports by University of Nevada, Reno, or UC Davis. These are all hot mix versus an evotherm warm mix. You can see the various mixing temperatures and compaction temperatures. Mixing temperatures were about 40 degrees to 60 degrees lower than hot mix asphalt. And there was dynamic modulus data available for all of these mixtures in the literature. And so I looked at, well, first of all, what's the impact of E star on the lower production temperatures? And this is E star at 20 C, which would be the effective fatigue temperature. And then I used a frequency of about, it was 42 Hertz, which I think corresponds to 55 miles per hour. As you can see, there's a pretty big change in E star when you reduce your temperatures anywhere from 14 to 30%. But when you look at what that impact is on the strain is the strain at the bottom of the AC layer, it's minimally impacted, and that's due to the layered elastic analysis equations based off of Boussinesq and Burmester theory, where it's really what's governing that strain calculation is the thickness squared. And so the modulus itself has somewhat of a minimal impact on the performance. And this dynamic modulus value and then this strain are then used to look at, in this case, 2 fatigue models. The top is from the Asphalt Institute from '82. The bottom one is the AASHTO Pavement ME, what's currently being used in there. And so based on these mixtures, I've got the strain using layered elastic analysis. I've got dynamic modulus from the literature. And then the air voids and volume of effective asphalt also comes from the literature. And I was able to make comparisons of number of cycles to bottom up fatigue cracking for either an evotherm warm mix asphalt pavement or the hot mix asphalt pavement. And so here's the fatigue life prediction equation using the Asphalt Institute model, assuming a 9 kip axle load. Here's the various cycles to failure. And then this is this expected life difference concept where I take the ratio of the warm mix N sub F divided by the hot mix N sub F. As you can see, these different mixtures give you different improvements in fatigue life. And so you see a range of anywhere from 6% to 23% improvement in expected fatigue life. On average, it's about a 14% improvement in fatigue life when making a mixture warm versus hot using the Asphalt Institute fatigue model. If we look at the model that's used in AASHTO Pavement ME, the values are slightly different, but that ranges from 12 to 41% in expected life difference. And so on average, you're seeing about a 26% improvement in predicted fatigue life using this model. And so in summary, for this example here, reducing your mixture production temperatures by 40 to 60 degrees Fahrenheit may improve the predicted pavement fatigue life by 14 to 26%. And so some questions to think about and ponder. And that is all And so I want to thank you again for your attention, and if there are any questions, we're here to answer them.
Okay, thank you very much. I've got a couple. We are running, a little short. We're going to be running a little short in time, but I'm going to ask the questions. And Brian and Dennis, Richard, and Jason, you can field them. The first question, let me get it out there, is, and I think this is more for Dennis, is your research and findings primarily related to the wearing course binder performance, or does it apply to all asphalt pavement courses?
This is Dennis. It somewhat applies to all paving courses, but of course they age at different rates. The surface, because of its exposure to higher temperatures, will age more rapidly than binders that are under 2-4 inches of pavement. That pavement acts as an insulator from not only the temperature, but from also some of the oxygen too. But so yeah. So it, like I said, it does reflect all binders in the pavements, but I would say in general, though, it probably is more related to the surface because of the direct aging that we have simulated on those binders.
Okay, next question. I don't know who should field this one. Let me ask us. I would like to see the data with 64V minus 22 binder. New York DOT uses a significant amount of 64V minus 22 and warm mix. I would expect even better performance. It would be interesting to see the difference versus 64S minus 22. And then the rest of the question is, we always face the issue of contractors complaining that 325 degrees Fahrenheit with polymer AC is too difficult to place even with warm mix. I tend to disagree and feel the issues with the chunks in the mix is better solved by using MTVs and rather the higher mix temperature. So anybody want to comment on that or answer that question? That's a good one.
This is Dennis again. I can provide maybe a little comment. We have done some work with polymer modified materials. One of the drawbacks is, though, that the industry, from a lot of the academia, from that standpoint, they've not really settled on what properties or what testing can be done on the polymer modified materials. As an example, delta TC with polymer modified materials can often indicate that the polymer modified materials will perform worse than the unmodified materials. And so that's just one example, and there are several examples, but it kind of boils down to, we just don't, from an industry standpoint, it's just not really settled on what to really look at for polymer modified materials from a performance comparison.
Okay, just to, go ahead if you want to add on to it.
Well, I was just going to say, now from a mix standpoint, maybe Richard and Jason can comment on that, but I was just talking about from a binder perspective.
Well, from a mix standpoint, the binder that we used in the data that I showed you was a 70-22, and it most likely had some polymer in it, and so that data kind of speaks for itself. I would say there's more work that needs to be done. I mean, It took Dennis a tremendous amount of time to generate the data that he showed you in this particular presentation, and that's always a question we get from people is like, oh, we'd like to see it with this binder. Well, that takes time. So, eventually we will have polymer modified data to add to some sort of a presentation like this.
Okay, we're going to run over a little bit here. I'll keep asking the questions. If you folks, you can stick on, we'll see if we can't get them all answered. Have you done any testing with binders and warm mix additives at the standard RTFO temperature versus non-warm binders, so you are comparing apples to apples?
Yes, we've done that too. And maybe that should be included as part of this study. So what we see is, of course, the lower temperature of itself improves binder performance, but the warm mix additive also shows an improvement, so that you get like a 2-component. Not only is it temperature, but it's actually the warm mix additive too that is favoring better binder performance with these lower temperatures.
We don't have any mixed data along those lines yet. There may be some of the field performance data, I think, that Jason has that could speak to some of that. But
Okay, I'll ask 2 more questions. If the DOT requires compaction at regular temperatures, does warm mix additive still show improved ideal CT numbers? Not a bad question. Okay, if the DOT requires compaction at regular temperatures, though, and I'm not sure what regular temperature.
yeah, what does regular temperature mean?
I mean, there is a range, PennDOT's range is, 2+ to 3+. So does the warm mix still show improved ideal CT numbers? So I guess the higher the mixed temperature, the lower the mixed temperature, what happens to the ideal CT numbers? Maybe that's, I'm way of saying it. Do you get better ideal CT numbers with greater or less tests? But I guess it's with or without warm mix. You'd have to ask the question, because that's pretty much what your presentation was about, I think.
Yeah, we showed the data that indicated, of course, that was lower temperatures and a warm mix. I did not have any data regarding just lower temperatures without a warm mix, if that is the question.
Yeah, your finding basically said that you can get better performance at lower temperatures with the warm mix additives.
Right. You'll see a trending upwards with regards to ideal CT testing, the crack index. Is it going to be significantly different? It's hard to say, because there's variability in that test. Although you'll see on average it begins to move, it gets higher, and that means you're taking into account the air voids of the samples and all that stuff too.
Roger that. The last question: what is your recommended warm mix additive? And I could probably say that's probably Evotherm, I would think. And at what dosage should they consider for high wrap and mixes, I guess 50% plus? Have you done any work yet with higher wrap mixes?
The short answer to that question is yes. We have done done a lot of work with higher wrap mixes. We've used we have a rejuvenator also that we use that has some warm mix capabilities built into it. But to answer that specifically, not off the top of my head do I have any data that I could say that I could point to that we have to answer that. I don't know, maybe Dennis or Jason can remember something that we've done in that regard.
Was it a 0.5% usually? And then if you increase the wrap, do you actually increase the amount of additive in the mix?
It depends. It depends on the mix. It depends on the wrap. So typically what we do is we recover the binder from the wrap and understand how stiff it is. And then you start there to determine what is actually needed. Sometimes it's, you know, you increase the warm mix. If it's a really stiff wrap, you're going to need something else besides just the warm mix additives, in my opinion.
It's like making a cake. If you change one thing, or then you got to change everything else.
So the answer is that it depends, and
It
you need to
depends.
test the materials prior to putting the mix together.
Well, that's all the questions. Brian, do you have anything you'd like to, to say to conclude the webinar?
I just want to thank everyone for attending, and I also just want to thank Jason, Richard, and Dennis for your presentation. You did a fantastic job, and I say this: if anyone has any more questions, please just don't feel free to email any of us, and we'll be happy to do what we can to answer them. But again, thank you for attending, and we just looking forward to being able to add more information to you at a later date. Thank you very much.
Yeah, thank you, Brian and Dennis and Richard and Jason for these excellent presentations. This data was, you've obviously done a great deal of work. And I was director of research for PennDOT too, and it's funny, you get to an end of a research project, and one of the recommendations from the researcher always is, well, we need to do some more research. So it's a perpetual thing. But I think with the asphalt pavement industry is we're always trying to improve our product. We're always working, we're not satisfied with what we got. And we are trying to increase performance. We are trying to make it more sustainable, more environmentally, acceptable and all those sort of things. And, but at the same time, we don't want to impact how good a product we have. In fact, we do want to make it perform better. So I want to thank you guys for doing this for Pennsylvania. I know we had a lot of people on from New York too, and some Virginia and other places around. I do want to just finish and say that if you want to learn, if you want to get educated, we have our conference coming up on January the 19th and the 21st. It's the 19th is from 8 to noon, and the 21st is 8 to noon. The 19th is more of our general session. We have the Deputy Secretary for Highway Administration for PennDOT. We got the CEO of the Turnpike. We got the Pennsylvania Division Administrator for FHWA. We got the President of NAPA, the National Executive for the Asphalt Pavement Alliance speaking. And then on Thursday, we have a lot of interesting technical presentations. And the final one on the day is Richard Willis from the National Asphalt Pavement Association is going to talk about something that's, I'm sure, Ingevity is going to be looking at too, is where we're going with putting plastic waste into asphalt. And you can see the rest of our upcoming events. So with that, I'll say thanks to everyone for your patience, for your perseverance here today. And we thank you for being part of the first PAPA webinar of the year. So that concludes the webinar. We have recorded this, and it will be posted onto our website for anyone who wants to come and sit through another hour and 45 minutes of presentation. So thank you very much.
Done.
Okay, everybody, I guess that's a wrap.
Okay.
So that went pretty smooth, I thought, everybody. Callie, if you're still on, thanks for your help. Donna, great job. Brian, thank you for lining the presenters up. That reminded me of Professor Gary Hoffman with those presentations. Gary enjoys that kind of information, and we appreciate you guys doing this for us. So I'm going to sign off. Everybody have a great day.